being equal, then this Jacobian matrix has this form. These two entries, ux and vy, they're equal. So they would be some number a. And then these two are negatives of each other. So they would be equal to minus b and b for some number b. So when your change of variables looks like that, what properties does it have? No, I don't expect you to know. I'm going to tell you. Okay. Well, a matrix like that, I'm going to rewrite it. So I'm going to pull out a factor of square root of a squared plus b squared. So now we're going to have a over this, b over this, and we have minus b over the same thing.
That looks like it.
Yes.
Let's see, we have a c on the outside, a over c, b over c.
Yeah, so what are these, how can they be described?
Sines and cos.
Yeah, sines and cosines of the same angle. So let's call this r. So we have r, cosine theta, minus sine theta, cosine theta. Well, this matrix, when applied to a vector, does a rotation counterclockwise through the angle theta. So when you have a change of variable that satisfies these conditions, all it is there's a stretching going on because of a factor r, and there's a rotation. But because that's all it does, it preserves angles. Okay. So what that means is a complex differentiable function, if you look at if you look at its graph, if you will, so if you have a little bunch of points in the plane and you see where they're mapped to, or if you take a curve and you apply the function to the curve and see what new curve you get, it preserves angles between curves. So, so what you have is called conformal mapping, which is one of the most interesting often applied aspects of complex variables. So mapping in such a way that preserves the angles between curves or lines. All right. So as my own complex analysis professor used to say, you don't get nothing like that from the reals. Something he liked saying.
He said it just like that?
Pretty much, yeah. Yeah. He said it a little more dramatically than that, but yeah. Okay. I should also mention that in my real analysis class, which is really the end of my honors calculus sequence, we were given a take-home final exam plus oral, so it was both, and it was on all this stuff. Yeah. Or I should say all this and more. So it was a bit challenging. Okay. Questions? All right. Well, and for those of you who are continuing on through math, that's pretty much the only complex stuff you're going to see. You probably, I guess you would see some of it in physics. Hopefully somewhere anyway, but okay. Alrighty. Now, differential forms. So we talked about all the operations on them, you know, how do you multiply them, how do you differentiate them, but what do you actually do with them? As strange as those operations are, they're actually meant to simplify things in the end, because we have this hodgepodge of vector calculus theorems that no one seems to remember. Green's theorem, Stokes' theorem, divergence theorem.
I mean, we kind of like remember them. We just didn't like being confused.
Oh, yeah, okay.
Yeah, maybe they were called like, the divergence theorem, that's a good one, but all the other named ones, if they were more descriptive of what the theorem does.
Yeah. Well, it's unfortunate that the divergence theorem is often simply called Gauss's theorem.
Sorry.
Okay, so suppose we have a one form, omega, p dx plus q dy plus r dz. Okay. So, if we apply the differentiation operator to it, then what's going to happen is you're going to have the differentiation operator applied to p times dx plus dq dy plus dr dz. There are other terms that come up where you're applying a differentiation operator dx, dy, dz, but as we saw last time, all of those are going to turn out to be 0, so not going to bother with them. But then p, q, and r are functions. So, and let's assume that they're components of a vector field f, which will also be used. Okay. So now we need to take the derivative of this one form p, and then the same thing with q and r. So we're going to have px dx plus qy, or sorry, py dy plus pz dz, all times dx, plus, similar for q, qy dy plus qz dz dy plus rx dx plus ry dy, this is tedious, rz dz dz.
Now you know how we feel.
Okay, I totally deserve that. Now, yeah, number 6, I know. Yeah. It's fun, interesting that it worked out that way. Was number 6 in the first exam bad? No, it couldn't have been, because it was 1, 5, and 10.
I think it was number 2 on the second, or it was number 6 on the second exam.
1, 5, and 10 were the hardest, yeah. So, all right.
Well, 1 plus 5 is 6.
Oh, okay then. Charles saves the day. So now, you got to multiply all these out, but when you have dx, bless you, that's going to be 0. So a lot of these terms are going to go away. So what you now have is py dy dx plus pz dz dx. In the first line, but you're going to have qx dx dy plus qz dz dy plus rx dx dz plus ry dy dz. But now we want to combine these, so we want to have these dx's, dy's, dz's in the right order. So some of these are now going to be negated. So we're going to have so dx dy times qx minus py. Is that familiar? Okay, dx dy. Then we have, okay, so the next thing we want is dy dz. Okay. So that's going to be ry minus qz dy dz. And then we have dz dx, so it's going to be pz minus Rx dz